Greetings to one and all. My name is Kausalya Nandan, Assistant Professor from the Department of Electronics and Communication Engineering, B.V. Raju Institute of Technology, Narsapur. The concept that we are going to discuss today is from the course of Electronic Circuit Analysis. The concept is about the feedback amplifiers. So fundamentally, the feedback amplifiers are used in the amplifiers for speakers and headphones to ensure clear and high quality audio sounds. Utilized in the medical equipment like ECG and machines to improve signal accuracy and reliability. Apart from that, these feedback amplifiers are used in the design of some communication systems where we design filters and amplifiers. So these are some of the applications of this feedback amplifiers. But why we should study this particular concept? So when we have the amplifiers, so these amplifiers generally will take the input signal, they do some process and then produce the output. So the output from the amplifier is estimated or is expected to have improvement with respect to the quality of the input signal. So that is, the signal strength can be increased, right? So when you are increasing the quality of the signal, so there could be a possibility of some errors that could be occurred in the output signal. So if you have to minimize these errors, the output signal will be taken back to the input, and again this is said to be processed. And this portion of taking the output back to the input is called as the feedback principle. Feedback principle or feedback concept. So to define this, so the feedback amplifier or the feedback, a sample of the output of an amplifier is given back to the input of the amplifier through a network, what is called as the feedback network. So here we can see the circuit of the feedback network. So where we have the amplifier circuit and we have the feedback network. So the output of the amplifier is taken here and it is given to the feedback network, and the output of feedback is again fed back to the input of the amplifier circuit, right? So this is how generally the feedback principle is said to be defined. Now based on the amount of the phase shift that was observed between the source signal, that is the input signal, and the feedback signal, we have two kinds of feedback, what are called as the positive feedback and the negative feedback. So to define them individually, what is positive feedback and what is negative feedback? So if the amount of the phase shift between the source input signal and the feedback signal is 180 degrees, so this is the amount of feedback between input and the feedback. If this is the case, then we call such kind of feedback as the positive feedback. On the opposite case, if the source input signal and the feedback signal both are in phase, then you call that particular feedback principle as the positive feedback. So defining this feedback concept, so we have two kinds of feedback. One is the positive feedback where the input and output are related with one another, and the input and the feedback system are related with one another in such a way that both of them are in phase. That kind of feedback is called positive feedback. And if there exists a 180 degrees phase shift between the input and the feedback signal, then that is called as the negative feedback circuit, right? Now from the feedback amplifiers or the feedback, basic feedback, these are generally used in order to ensure that we have some kind of improvement with respect to the quality of the output signal that is existing earlier, right? So we observe that with the utilization of this feedback principle, there are some parameters that will be affected. So the first parameter that will be affected upon interaction of the feedback is your gain. So the gain will be generally reduced when you implement it with respect to the negative feedback. And number two, it is distortion and noise. So these two parameters will be decreased when you apply the feedback principle to your amplifier circuit. Similarly, when you have to apply your amplifier circuit for a large range of frequencies, then this feedback will help us. So directly or indirectly, it means that when you apply feedback, the bandwidth increases. So generalizing, so the main objective of this particular course is to understand what is the principle of the feedback in the electronic circuits. Principle of feedback in the electronic circuits. This is the first objective that we observe with respect to this particular concept of the feedback amplifiers. Then you will come to have a clear identification or justification in designing and analyzing the feedback amplifiers. And third important point that we have is you will be able to develop problem solving skills in the electronic circuit analysis. Develop problem solving skills in the electronic circuits. So these are the objectives of this particular concept, that is the feedback amplifiers, right? Now what is that we expect? We call it as the outcome. Once you complete this concept or once you learn this concept, you will be expected to understand the feedback topology. This is the first outcome that can be expected when you learn this particular concept. And number two, you understand the effect of feedback on amplifier parameters. So that is what we have discussed in the previous slide, where we have defined with the parameters as gain, bandwidth, noise, distortion, etc. So this is the outcome that can be expected once you learn this particular concept of the feedback amplifiers. Now let us consider the generalized feedback amplifier network. So this is the basic amplifier. So if the output of the amplifier is fed back to the input through this feedback network, right? So assume that we are providing a source voltage here, Vs. So to the amplifier, the amount of voltage that is driven will be Vi, input to the amplifier, right? So the output will be V0. So a portion of this output will be considered here. So V0 and Vf will be the output of the feedback amplifier. So the input to the feedback will be V0, which is the output of the amplifier, and Vf is the output from the feedback network. So these two are related to one another with respect to the relation Vf is equal to beta times V0, where beta is called as the feedback factor. Similarly, here the amplifier has a gain of A. Now, the gain with respect to the amplifier AOL, that is the open loop gain, only the gain considered with respect to the amplifier will be the output voltage by the input voltage. So that is V0 by VL. V0 is the output from the amplifier and Vi is the input to the amplifier. So V0 by Vi is the gain of the amplifier. Similarly, a closed loop gain, that is including the feedback network. So then it will be output voltage with respect to the source voltage. So gain is the ratio of output parameter to the input parameter. So output parameter with respect to the open loop condition, that is only with respect to the amplifier, is V0. Input voltage with respect to the amplifier is Vi. In the same lines, when we consider it in the form of the closed loop, that is when the feedback network is also included, the output voltage will be V0 and the input voltage will be the source voltage Vs. And then the feedback factor, as we have defined here, beta is equal to V0 by Vf. So where V0 is the input that has been provided to the feedback network and Vf is the output from the feedback network. Now, at the input of the amplifier, we can define the voltage Vi is equal to Vs minus Vf in case of the negative feedback amplifiers. As we have defined that there will be a 180 degrees phase shift between the input and output. So the input voltage that will be provided to the amplifier will be the difference between the source voltage and the feedback voltage. So Vs minus Vf. So this is equal to Vs minus Vf is beta times V naught. So Vs minus beta times, so V naught from the first equation, AOL into Vi. Now simplifying this parameter, so we have Vi plus beta AOL into Vi is equal to Vs. So if Vi is taken common, 1 plus AOL into beta is equal to Vs. So now ACL from the previous equation, ACL is equal to V naught by Vs. So where V naught by Vs, as we have defined just here, so it is Vi by 1 plus A naught into beta, AOL into beta. So V naught by Vi, which is the ratio of output voltage to the input voltage, that is the gain of the open loop. So by 1 plus AOL into beta. So the closed loop gain is equal to open loop gain by 1 plus a open loop gain times of the beta. So, or in other simple functionality representation, we represent this AF is equal to A by 1 plus A beta. So, for the negative feedback amplifier, the feedback gain is said to be given as A by 1 plus A beta. So, that means the gain of the amplifier reduces by a factor 1 plus A beta when you apply negative feedback to your amplifier circuit. So, similarly, in case of the positive feedback amplifiers, so with respect to the positive feedback, if you implement it in the same lines, so your Vi will be Vs plus Vf. So in the previous case, it is Vs minus Vf as we have seen here. But now with respect to the positive feedback, it will be, because the input and output will be in phase. So you have the connectivity between the source voltage and the feedback voltage as Vs plus Vf. So accordingly, the gain with respect to feedback will be A by 1 minus A beta. So this is the feedback gain when the positive feedback is said to be applied. Now let us discuss another important concept here, what is called as the block diagram of the feedback amplifiers. So in the block diagram of the feedback amplifiers, so initially we have the basic amplifier, then we have the feedback amplifier or the feedback network. So to the amplifier, we need to provide the signal. So we have the source here. So then we have the mixer circuit which combines the output of the feedback with the source and provides the input to the basic amplifier. Then from the basic amplifier, we have a sampler circuit, so which samples a part of the output and that will be delivered to the feedback network. So then you have the output network here. So this is the basic block diagram of the feedback amplifiers. So now let us see one by one. The first one is the source. So sources can be of two categories. One is an voltage source with a series resistance Rs, or the source can be a current source with a shunt resistance. So this is Vs, the voltage source, and this is Is, the current source. So two kinds of sources can be provided at the input. One can be the voltage source, the other would be the current source. Then the second part we have is about the feedback network. So in general, the feedback network would be a resistive network. Feedback network is a resistive network. This is the second one. Number 3 is the basic amplifier. Now, what does it mean by the basic amplifier? So, amplifiers could be of 4 different categories. So, that could be voltage amplifier. Number 2, current amplifier. Number 3, transconductance amplifier. And number 4, it could be the trans resistance amplifier. So this depends on the relation between the input and output parameters that could be expected from the amplifier circuit that we have been designing. So if the input is an voltage and the output is also an voltage, then the gain will be given as EV is equal to output voltage by input voltage, and then such kind of amplifiers result as an voltage amplifier. In the same lines, so if the input is current, so this is II, and the output is also current, then you define that the gain expected to be will be the current gain. So the amplifier correspondingly will be the current amplifier. In the third case, we have this is the transconductance amplifier. So what does it mean by transconductance? So the output should be the current and input is voltage. So if this is the expectation from the amplifier, so the output is current that is expected from the amplifier, when provided the input as an voltage, then you define that as a transconductance amplifier, and opposite to this case you have the trans resistance amplifier where we have the output is voltage and the input is current, right? So accordingly, we have these 4 basic kinds of amplifiers that can be utilized in the design of our feedback topologies. Now, the 4th case that we have is how we establish the connectivity between the basic amplifier and the feedback network. So we have been saying that the output from the amplifier has to be sampled and it has to be provided back to the input through this feedback network. So a sample of the output is taken and given to the feedback network using a circuit what is called as sampler. So sampling can be again of 2 kinds of parameters that can be sampled, as we can see with respect to the amplifier outputs. It could be either current or voltage that is being obtained as the output from the amplifier. So accordingly, you can either have an voltage sample or you can have a current sample that can be used to feed the input of the feedback amplifier network. So if voltage is being sampled, it is called voltage sampling or shunt sampling, right? So the circuit looks like this. So this is the amplifier and this is the feedback network. So this is the load. So this kind of representation will be considered with respect to the voltage sampling. This is also called as the shunt sampling. Opposite case we have is the current sampling. So this is also called series sampling. Current sampling or the series sampling. So here fundamentally we have the amplifier network and the feedback network. So between these 2 at the output we have the connectivity established in the form of a series network. So this is RL. So this is how the output will be connected with respect to the feedback network. Then this output has to be fed back to the input using the mixer circuit. So we mix the feedback signal with the input signal. Now how do we mix this? Again, we have 2 kinds of mixing. One is called as voltage mixing, another one is current mixing. right? So here we follow the opposite principle to that of the sampling. So voltage mixing will be series mixing and current mixing will be shunt mixing, right? So accordingly, the circuit that can be represented is like this. So this is the amplifier, this is the feedback network. Now at the input, because this is voltage that is being considered as the source input, this is mixed in series connectivity. Similarly, with respect to the current mixing, so this is called as the shunt mixing. So this is the amplifier, this is the feedback network. So between these two, we have the connectivity established in this way. So this is the current source that we have. So finally, so this is how we generally go with the connectivity of different components or the different circuit elements that we have in the feedback network. So initially we have started with the block diagram of the feedback amplifiers, where we have the source, mixer, basic amplifier, sampler and the output network, and the output and input are connected through the feedback network. So just refining once again, we have two kinds of sources. One is the voltage source, another one is the current source. Then the feedback network, generally most of the feedback networks are resistive in nature. Then we have different kinds of basic amplifiers as the voltage amplifier, current amplifier, transconductance and transresistance. So which are said to be obtained with respect to the input-output relations that the amplifier exhibit. Right? Then we have the sampling network, where the output that is sampled to be provided to the feedback network. So it is done through the sampling network or the sampling circuit, where you have the voltage sampling, also called as the shunt sampling, or we have the current sampling, which is also called as the series sampling. And finally, at the input, when this sampled output has to be mixed through the amplifier through this feedback network. So we do it in two different ways. One is the voltage mixing, or it is called as the series mixing. And then we have the current mixing, or also called as the shunt mixing. So this is how the generalization of the feedback amplifier circuit is said to be defined. Now accordingly, with respect to the sampling and mixing processes, we have four kinds of topologies that would be defined with respect to the feedback amplifiers. Four topologies. So these are called topologies, or the feedback amplifier circuits that are established with respect to the sampling and mixing parameters that we have. So the first topology that we have is voltage series feedback amplifier. Number two, voltage shunt feedback amplifier. Number three, current series feedback amplifier. And number four, current shunt feedback amplifier. So four different combinations of the input output sampling and mixing parameters that would be possible, and accordingly we have four kinds of topologies. So here the actual meaning of this particular name to the amplifiers that was given is like this. So we are considering the voltage sample from the output and we are mixing it in series with the input. So the first parameter of every stage here defines the output or the sampling parameter, and the second parameter defines your mixing parameter or the input parameter. So the voltage is taken at the output and it is mixed in series with the input. So that kind of amplifier topology is called as voltage series feedback amplifier. So if voltage is taken at the output and mixed in shunt at the input, so then we call that as voltage shunt feedback. If current is taken at the output as a sample and it is mixed in series with the feedback amplifier at the input, then we call that as current series feedback amplifier. And finally, the same current is taken at the output sample sampler, and it is mixed in shunt with the input amplifier, input of the amplifier, then we call it as the current shunt feedback amplifier. So this is how the topology is to be defined. And in other way, these amplifiers can also be defined in this way. So this is also called as voltage series feedback amplifier, is also called as series shunt feedback amplifier. So that means this is the input and output mixing and sampling parameters again that we are considering. So here voltage is mixed because this is voltage is taken here. So that is mixed in series. So in the mixing we are considering like this, and it is because voltage is taken from the output. So we define the sampling parameter as a shunt parameter. So series shunt. So here we are defining input as the first parameter, output as the second parameter. So the other way of defining this feedback topologies is like this, right? Similarly, this is input is shunt, output because that is voltage, again output is also shunt. So shunt feedback amplifier. And the third case, we have input, we have series, output is current. So as the input is mixed in series, output is current. So output is considered also in series. So this is called series feedback amplifier. And finally, the fourth one, it is, so input is shunt, output is series, because output parameter is current here. So output is series. So this is called shunt series feedback amplifier. So this is how we can even define the feedback amplifiers with respect to the input-output relation that exists between the mixer circuit and the sampling circuit. Right? So we will conclude it for today. We will continue our discussion with respect to the in-detailed analysis of these feedback amplifiers, where we see the behavior of the amplifier, or we observe the parametric analysis of these amplifiers with respect to the gain, input and output impedances for these four topologies. Right? So thank you. Thank you for giving the opportunity.
Like, share and subscribe. Hit the bell icon for more updates.